Hello everyone. So the goal of this lecture is to give a quick overview of Fourier analysis of the Boolean cube. We do not need a lot, or at least in principle, do not need a lot. So the goal is to establish some notation and a few basic properties so that and reuse them. So we're going to discuss the Fourier analysis. On the Boolean cube. If you're familiar, which I expect that a good fraction of you might be, please skip this lecture. We are only going to cover the very basic of it. And what is a Boolean function first? So you're going to work with more general. Let me say a function on the Boolean cube. Be it Boolean or not. On the Boolean n cube. So here it's going to be a function f from f2 to the n to the reals here. And it's very convenient when you're dealing with Fourier analysis to work on the plus minus one basis. So here we would have binary strings, right? F2 to the n, but sometimes it's very convenient to map a 0 to a 1 and a 1 to a minus 1. And this is going to make so you're mapping using the non-trivial character of FF2, right? And it's going to respect the group operation. So if somehow, if you're applying the XOR here, this is going to be equivalent to take the representation and doing pointwise multiplication, right? So this is equal to 1, and this is equal to minus 1, right? So it respects, right? Okay, very good. And what we need to define. So in this language, so instead of working here, it might be more convenient to think that we are working on plus minus 1. To the n, mapping to the reals, it's completely equivalent. And it's convenient to define a collection of functions. So for each set, subset of n, we can define the character. The character related to this, and Ks apply to, I don't know, here we are going to have some input, but it's going to be a function in the cube again. And let's operate in this plus minus 1 representation. And here it's going to map to plus minus 1s to the reals, but more specifically to plus minus 1s. And then chi of s at some input, and this input is some x1, x2, x2, etc., all the way to xn. This is simply the product. So this is, by definition, the product of the guys I belonging to S of xi. So this is a character. And in this space, it's also very convenient to define a distribution, right? So we have the verts of the cube, this plus minus 1 representation, and then you can endow this with the uniform distribution. So we're going to be working essentially with the uniform distribution. And one very easy claim is that suppose now that we take two sets, S and T, contained in N. Okay, so let me first do a smaller lemma. What is going to be the expectation of this guy here. So if you take a random string according to the uniform distribution, it's a perfect product distribution, right? So here you have x1, do h xn, uniformly plus minus 1 to the n. And now let's consider the chi-s that we had before, etc. Xn. And by the definition, this is the product, right? Very good. And since it's a product distribution, so here I belong to S, xi, this splits into the product of the expectations of xi, I belong to S. And if S is different than the empty set, then there is at least one element here, and its expectation is going to be 0. So this evaluates to 0. Very good. So expectations of characters that are not real, the non-empty character, they evaluate to 0. And of course, if S is equal, and if S is equal to the empty set, it evaluates to 1. So we can summarize this as follows. Expectation of S under the uniform distribution is 0 if S is different than the independent set, the empty set, and it's 1 otherwise. Very good. So we have this very easy thing here, and we can endow this space with an inner product, right? So if you have two functions here, let's say we have f and g from plus minus 1 to the n to the reals, and the inner product is the inner product under the uniform distribution. So by definition, the expectation of x uniform plus minus 1 to the n fx gx. Very good. And the first little claim of the Boolean Fourier analysis is the orthogonality of characters. So under this inner product, so the collection of characters, chi-s, s containing n, forms an orthonormal basis. Orthonormal normal base of functions. The proof is very simple, as you might have seen. So suppose now that we take two characters, s and t, contained in n, so that they are going to be indexed in two characters. And if you consider the inner product of the two, so here we have chi-s, inner product with chi-t. This is nothing more than this expectation here. Chi-s of x is uniform, chi-t of x. So very good. And whenever there is, if s and t share a variable, this variable is going to appear in a square form. And if you have a plus minus 1 variable that you're squaring, it becomes 1, right? So everything that's in the intersection here of s intersection t is going to appear squared because it appears from this guy, so it becomes a 1. So the only elements that survive are the elements that are in the symmetric difference. So here we have the two sets. This is the intersection, this is S, this is T, and only elements that only appear in S and elements that only appear in T, they survive, right? So it's as if you're looking at the expectation over X of a character in S symmetric difference T of X, right? Very good. And this is going to be, if this is we have seen before, this is going to be the indicator of S symmetric difference being the empty set. If they happen to be the, or perhaps it's cleaner to write this way, an indicator of if they are the same or not, right? This is an equivalent way. If they are the same, then the symmetric difference is the empty set, and the empty set has expectation 1. Otherwise, it's not the empty set, the symmetric difference, and then the expectation is 0. Very good. So it means that's so we just proved that the characters form an orthonormal basis. This is their product, and that's extremely convenient, because if you have any function, we can write in terms of this basis, right? If you have a function on the Boolean cube to the n, to the reals, we can decompose it, we can write it in this basis, and there's going to be a summation here over all the characters, and then here we have some coefficients that we get times the character s. Okay, so I think that we have some f of x and the character here, and those coefficients are real scalars, right? So this is some scalar, and that's a Fourier coefficient associated with this character s. And how do you compute this guy? That's very simple. So we can take our f, and then we can apply the inner product with this chi s. And then here, since this follows from, because we have a base, so the characters, they form an orthonormal base, or just a basis, characters form a base. There is a unique way of writing this form. Characters form a basis. Very good. And then you have this. Okay, very good. S. N. Okay, chi s, x. And then here we have our chi s. Chi s. Let's suppress this part. Let's suppress this part. Very good. We compensate a little bit. So we have this inner product. The inner product is linear, right? So we can move this the summation to the outside, right? Need to change the name of the variable to not conflict with this one, because we're summing over all possible choice of s, and this s is fixed. And the only guy that's going to survive, because the characters, they are orthogonal, right? It's going to be when this choice of s is the same as this one, right? And then you get precisely this. So it means that the coefficient that we get out of this is precisely this inner product here, right? So we conclude this, right? Using the fact that the characters form an orthogonal basis. Very good. So now we know, given any function, you know how to expand this in Fourier basis. Extremely simple, and it's going to be extremely useful, because I don't know, that at some point someone said that one of the most powerful things, at least in his field of applied mathematics, is you have an object, and then you go to a different representation that's completely equivalent, and you do the operations there, then you go back again to the original domain. So Fourier analysis is of this form, right? You have a function on the vertex of the Boolean cube. We go to a different basis of function. It's encoding exactly the same function, but that perspective might be quite illuminating for some proofs. And that's why we adopt it here. And there are a few properties that might be quite useful. So one property is called the Plancherel. And in this form, it's just a fancy way of evaluating inner products. So suppose that, as before, we have two functions from the Boolean cube to the reals, and you'd like to compute their inner product, f and g. Very good. And the claim, so this is a Plancherel. The claim is that this is simply the summation over all sets of their Fourier coefficients. That's an extremely useful fact. Sometimes it seems completely trivial, right, from what we have done, but it's extremely handy. And let's see a small proof in this case. So what is f? We can expand f in so we have f in the product G. Let's expand the 2 in the Fourier base. So this is going to be a summation of s, f hat of s, chi s. And then we do the same thing for G. So this is going to be a summation. Let's give another name, T, of G of T hat. That's a Fourier coefficient, and chi T. And the inner product is bilinear here. So we should have that's very similar reasoning from before, S and T. They're both subsets of N, Co. And then we have F hat of S, G hat of T, and then we have chi S, chi T. And that you already know by since characters they form on orthonormal basis. This is going to be 0 unless S equals to T. And then we get this nice summation. So this force S being equal to T. And then we have this little thing. She had, we have this. Very good. And one particular case is when you're applying this particular case. Case that's known as Parseval. So not flipping Plancherel and Parseval, but I hope I'm not. Is when you take f, the inner product of f with itself. Right? And then, very nice, you get the summation of the Fourier coefficients squared. Very good. When the two functions are the same, we get this. All right, so that essentially covers a lot of the things that you want to say. One important notion of the complexity of a character is the degree, right? So a character is sort of a monomial, and you can look at how many, what is the degree, right? So and the degree is precisely the size of the set. So we suppose that you have a chi-S, and S is again the subset of the elements here. Then the size of the set is called is the degree. Is the degree of this character. Degree. And typically we think that low degree functions are less complex than high degree functions. High degree functions might oscillate more, right? Faster. And yeah, so that's a notion of complexity, right? It's the degree. Let's see if I want to say anything else about the basic properties. Possibly not. So the goal here was to introduce a little bit of notation about characters, to say that functions in the Boolean cube, they admit this equivalence nice expansion in terms of these alternative bases, right? That you have the characters that are orthonormal under this inner product, and that one can compute inner products, and instead of computing in the original domain, you can compute in the Fourier domain, and that's a triviality, right, in the Boolean cube to establish, but it's very, very handy. And that's essentially the theory of Boolean Fourier analysis. Of course, to be able to extract interesting properties and so on, you might need more, but this at least establishes the required language to parse and understand these objects. Okay, so thank you very much. Stop here.